So in this video, we're going to be using Young's double slit. And Young's double slit is very important because it can be used to demonstrate the wave behavior of light. You need to be able to use these two formula, d sine theta equals m lambda and delta y equals wavelength times by length divided by d. And I'll explain what all this stuff means as we go through the video. There's a whole bunch of things you need to be able to describe, sketch, explain, and be able to solve problems. And I'll go through them side by side. So the first thing is, now Young was experimenting with two double slits. So if you expose some sun rays on two thin parallel slits and you allow the sun ray to pass through, the particle theory for what would happen is, if the light were too little, if light was made up of particles, then if you put a particle through a small gap, it's just going to follow the small gap. And you would expect two thin little bands to occur. That's what you'd expect. However, what happened when Young illuminated light on two double slits is he got this pattern here. He got a bright band in the middle, and then a bigger gap, bright band, bigger gap, bright band. So this is the pattern he got. And we can actually use the wave behavior, we can use wave properties to explain this pattern. So this is a Young's double slit interference pattern. And I'll show you how it works on the next couple slides. So, because Young didn't have a laser yet, so I got you to watch that video. Now, what we're going to be watching, what I'm going to be explaining here is slightly different to the laser one, because on the laser one, what you would have noticed is that there was dots. So there was a bright dot in the middle, and then a gap, and then a smaller bright dot, and a gap, and a dot, and you would have had a bunch of dots. That's because a laser beam is a single beam of light. Now, what Young did is, lasers weren't invented yet, so what he did is he passed not a coherent light source like a laser. He passed light through a single slit, and then that single slit hit the double slit. Now, it hit the double slit in phase, so only a single, so light went through here. It diffracted because it's a gap and it was light, and then there's, it might be on the next slide, yeah. So it went through the gap and it diffracted, and it spread out, and it hit the two double slits in phase, okay? Because they traveled the exact same distance, the two double slits, and now they were in phase. And so then what happened is, it basically hit the two double slits as two coherent light sources. So now the two double slits were two coherent light sources in phase with one another. And then once the light passed through the double slit, it again diffracted and it spread out. And this one also diffracted and spread out. And what you had was, there's regions of, or points of constructive and destructive interference. And when it hit the screen, you got bright bands of light, and then there was darkness, and then there was a bright band of light, and darkness, and a bright band of light, etc. Okay? So that's what happened. Light was passed through the single slit, hit the double slit in phase, then diffracted, spread out, and then on the eyepiece, he observed this interference pattern. And this could only have occurred if light was actually a wave and diffracted and spread out and underwent constructive and destructive interference. So that demonstrated the wave behavior of light. Now, it shows, so sometimes they're called dark bands or fringes. So there was dark brightness in the middle because it underwent constructive interference, and then darkness because it underwent destructive interference, and then constructive, destructive, constructive, destructive. Okay, as it hit the screen inside the little eyepiece. Now, I thought I put the delta y. Yep. So on your formula sheet, there is an equation that involves delta y, and delta y is just the distance between two adjacent, so the center points of two adjacent bright fringes or bright bands. It's also the distance between two adjacent dark bands as well, but usually we use the center of bright bands, a bit more defined. Now, the intensity distribution for a two-slit interference of monochromatic light, so a single light source, a single frequency light source, that was important. It did have to actually be a monochromatic light source. Otherwise, it never would have been coherent when it hit the double slits. But it created this pattern here where it was bright, then dark, then bright, then dark. And here you need to be able to sketch the intensity distribution for a two-slit interference of monochromatic light. So max amplitude right in the center of the screen, and then it sort of went a bit fuzzy, and then minimum negligible, like zero intensity darkness, and so on and so forth. With the laser beam, you would have seen this graph, but you would have had a much higher intensity in the middle, and that occurs with a laser. Realistically, it does occur with this as well. It's brighter in the middle, and then darker, and then a little less bright, and so on and so forth. But this center area is fairly uniformish. So the textbook uses this fairly uniform intensity distribution. So you do need to be able to sketch this graph. And then this is one wavelength away because the path difference I'll explain the path difference on the next. Well, I've already explained it in the past. So I'm not going to exactly explain this graph, but I have explained it in the previous video. So as the two light sources, so again, monochromatic light source, single slit, diffracts, hits the two double slits in phase, they then diffract further, and then they constructively and destructively interfere. Now, directly in the center, there's going to be constructive interference because both light waves have traveled the exact same distance. The path difference is 0 between these two light sources. So they hit this center screen here with no path difference, so that it constructively interferes in the middle. Now, this point here, let's say that this is the 1, so this would be m equals 1 here. This is m equals 2, this is m equals 3, and this is m equals 4. So here, what we're expecting is a path difference of 4. So from here to here, there must be a path difference of 4 wavelengths in order for the constructive interference to occur here. So this point here, from here to here, and here to here, we're expecting 1 wavelength of path difference in order for constructive interference to occur here. And for this point black beam here, it's going to be, so from here to here and here to here, we're expecting a path difference of half a wavelength in order for destructive interference to occur. So using trigonometry, we can get that this path difference, so if D is the distance between the double slits, and the angle is the angle from the center of the double slits to where the constructive interference is occurring, then using some trigonometry, we can get that this path difference here is d sine theta. And I'm not going to explain this here. You don't need to be able to do the Young's double slit derivation. Okay, but you do need to be able to use this equation that d sine theta equals m lambda. So on the next slide, I explain what each one means in more detail. So d is the distance between the double slits. The angle is the angle between the center of the double slits and the position on the screen. M is the number of wavelengths in the path difference. So if it's as I said before, if it was the first bright band, then the path difference M would be equal to 1. If it was the second one, it would be M equals 2, M equals 3, and so on. So M is the number of wavelengths in the path difference. So for constructive interference, it would be integers of 1, 2, 3. If it's destructive interference, it would be half values. So half or 1.5, 2.5 for destructive interference. So lambda is just the wavelength of the light source. Delta Y, as I've already explained, and it's not on this diagram, but delta Y is the separation between two adjacent maxima or two adjacent minima. And then L is the length from the double slit to the screen, and that's in meters. Everything's in meters. or degrees. So it is important that your angle is in degrees. So as I said, well, one of the things you need to be able to do is you need to be able to determine the wavelength of light using these equations. So what you can do is you can, if you've got some sort of light source, you can pass it through the single slit, then hits the double slits, diffracts, interferes, and causes the interference, Young's double slit interference pattern as seen here. What you can then do is you can measure the distance between adjacent maxima, or between adjacent bright bands, and you can find out delta y. But in order to reduce random error, what you actually would do in an experiment is you would measure across multiple, because it's a bit hard to define exactly where the center point is. So if you measure across multiple and then divide by how many you've gone across, you can find delta y, and that's going to reduce the effect of random errors. So we're going to do 3 quick examples. We're going to first determine the wavelength of a monochromatic light source from measurements of the two-slit interference pattern. So here we have a two-slit interference pattern. It's produced using monochromatic light. The distance between the double slits, okay, tiny, 2.45. So the double slits, remember, so this distance here, the distance between the double slits, and that was 2.45 times 10 to the minus 4 meters. And the slit to screen distance is 2.8 meters. So from the double slits to the screen, where the interference pattern is illuminated, is 2.8 meters. So that's L, and this is D. So a student measures the distance between 5 maxima. So between 5 lots of delta y is going to be 3.5. So 5 lots of delta y is 3.5 times 10 to the minus 2. So delta y is going to be 3.5 times 10 to the minus 2 divided by 5 to get what delta y is. So delta y is going to be, get my calculator out. I can do that. It's 3.5 divided by 5 is 0.7. So it'll be 7 times 10 to the minus 1. Nope, I went the wrong way. Good thing I checked. Brain is not switched on. Of course it's going to go the other way because it's going to get smaller. Okay, calculate the wavelength of the monochromatic light used to produce this interference pattern. So we've got delta y, the distance between 2 adjacent maxima. This equation doesn't have it in it, only this one does. So we need to rearrange this for lambda because we want the wavelength. So the wavelength is going to be equal to, we need to multiply by the d and divide by the L. So the lambda equals delta y times d divided by L. And then it's as simple as substituting in our values. So delta y is 7 times 10 to the minus 3 multiplied by d, which is our double slit distance, or the distance between the double slits, and then divide by the screen to slit distance, which is 2.8 meters. And if you type that into your calculator, you're going to get 7 times 10 to the minus 3 times 2.45 divided by 2.8. So you get that the wavelength of this light was 6 point, and it's 3 sig fig in the question above, so it's 6.125, but that 5 will round the 2 up to 3, so it's 6.13 times 10 to the minus 7 meters. So, 2 more examples. In this one we have a red laser, 628 nanometers. So nano is times 10 to the minus 9. It's used to illuminate 2 narrow parallel slits. Interference pattern is 3 meters away. The distance between, so we've got L, we've got wavelength, and we've got the distance between the adjacent slits is delta y. Calculate the distance between the parallel slits used to form this interference pattern. So we're actually looking for D. D is the distance between the parallel slits. So what do we have? Which equation? We've got delta y again. So we've got delta y. Do we have L? We've got L. And we've got wavelength. So we've got everything but D. So to rearrange this equation, we just need to get D to the top. So we're just going to swap these. And we'll get that D is equal to delta y, lambda times L divided by delta y. And then that's simply just substituting in. We'll get 628. And then nanometers is times 10 to the minus 9 multiplied by L, which was 3, divided by 1.5 times 10 to the minus 2. And if we type that into our calculator, 628 x to the minus 9 times 3 divided by 1.5 x to the minus 2. We'll get how many sig figs do we have? 3 again. 1.26 to 3 sig figs times 10 to the minus 4 meters. So very, very small. So less than a millimeter, 0.126 of a millimeter. Very small separation between the double slits for these interference patterns. Now, the red laser is replaced with a blue laser. So that was a red laser. Now we have a blue laser. When the blue laser is used, the angular position of the fifth order maxima. So fifth order, these are referred to as orders. So if we go back to this, here, this is m equals 0. This here is m equals 1, and that's the first order, second order, third order, fourth order, etc. So this is m equals 1, m equals 2, m equals 3, m equals 4. So in this question, we had the fifth order maxima, so the fifth one across. So this basically just means that m is 5. And this angle is 1.04 degrees. Because remember, we're 3 meters away, so if we have our double slits, and then we have our screen, this is 3 meters. So even just the fifth order one, the fifth one, m equals 5, is going to be a very tiny angle of 1.04 degrees. So calculate the wavelength of this blue laser. So we're trying to find wavelength. So we've got m now, so we're going to need to use this equation here to find the wavelength. So we're going to rearrange this equation for wavelengths. So we're going to have wavelength, and then we're just going to need to divide by the m. So it's going to be d sine theta divided by m, which is going to be d, which we just calculated as the double slit distance. Usually we have this written on our little double slits. They're usually manufactured and it's written on there what the double slit distance is, times by sine of the angle. So the angle is something that you often, if you want to do it this way, you would be required to measure, but it's a little bit difficult. That's why I usually measure delta y, like in the last example. Delta y is a bit easier to measure than the angle, because the angle is usually quite small. And then divide by m, which is 5. So remember, your calculator needs to be in degrees mode in physics, always. And we're going to get the wavelength of light is 4.57 times 10 to the minus 7 meters. And that's actually, if we were to get it back into nanometers, that's actually 457 nanometers. And if you check the wavelength of blue light, that is correct. So one more example. In our third example, we have a two-slit interference pattern. A two-slit interferometer. That is this. Interferometer is the technical name for this. So we have a two-slit interferometer, has a slit separation of 5. So that's D. A slit to screen distance of 40 centimeters. So that's L. It needs to be in meters. Light has a wavelength of nanometers, so that's times 10 to the minus 9, is used to illuminate the apparatus. An interference pattern consisting of equally spaced bright and dark fringes is observed on the screen, as expected. Explain why a bright fringe is observed at the center of the screen. Well, why do we have constructive interference at the center of the screen? Well, the light travels an equal distance and it undergoes constructive interference because the path difference is 0. And the waves arrive in phase and constructively interfere. So, explain why bright fringe is observed at the center of the screen. So, coherent light from the double slits has a path difference of 0 as it travels the same distance, and undergoes constructive interference resulting in a high amplitude and bright fringe. So calculate the angle of the third order maxima. So what do we have? Calculate the angle of the third order maxima. So third order maxima is m. So basically we're trying to find the angle. Okay, so if we have our double slits, we have our screen, we want not the one in the middle, that's m equals 0, m equals 1, m equals 2, m equals 3. We want the angle from the center of the slits to the center of our bright band here. So that's the angle we want. So our choices of equations, we've got d sine theta equals m lambda, and we want to find this angle here. So to rearrange this equation for theta, we need to divide both sides by d, and then take the inverse of sine of both sides. So we're left with theta equals m lambda, sorry, I should do sine to minus 1 first. Sine to minus 1 of m lambda over d. And we have m, which is 3. We have lambda, which is, do we have lambda? Oh yeah, the wavelength of light. And we have d, our slit separation. So if we type that into our calculator, we'll get sine to minus 1 of 3 multiplied by 485 times 10 to minus 9 with nanometers, divided by d, which is 5 times 10 to minus 5. And if you type that all into your calculator, (3 times 485 x to the minus 9 divided by 5 x to the minus 5 sine to the minus 1 of that. So you get an angle. So the angle of the third order maxima is 1.67 degrees for 3 significant figures. So have a go at the exercises outlined below. Cheers.